All right, here we go. This is going to be an extra credit video, section 3.8, absolute value functions. It's kind of a continuation of the 3.7, which was the piecewise and step functions. So it's looking at something that's not a straight line, but ties back into what we've been covering. So first of all, just a quick review of absolute value. The notation for absolute values in general is just double, long, straight, vertical, parallel bars. And you're taking the absolute value of whatever's inside. So it could be a number, it could be a variable, it could be an entire function. And the absolute value meaning, what these bars mean is how far away is the thing inside from zero? Or if it's a number, effectively make it positive. Because for example, some examples, if you have the number 5, how far away is the number 5 from zero? It's a distance away of 5. So effectively just keep it positive if it's already positive. But on the other hand, if you have a negative number, like for example, -7, and you take the absolute value, how far away is that from zero? It is 7 units away. So when you're asking how far something away is, it doesn't matter if it's to the left or to the right, it's a numerical distance away. So you just basically make it positive. If you have variables on the other hand, like the absolute value of x, you can't simplify that without knowing more about it. Is it part of an equation? Are you trying to rationalize something? So if you have absolute value of a variable, you just kind of leave it until you get to the next step, depending on what you're doing with that. So that's what it is for individual numbers or individual variables. But what about an entire function, right? So let's take a look at some functions and some graphs and see what's going to happen. Well, let's go back up here. If we have the equation y equals absolute value of x, suddenly this means something. So every function value or point on the graph that's already positive stays the same. So those absolute value bars don't do anything to the section of the graph that's positive. But any location on the graph where it would have been negative, when you take the absolute value, it becomes positive. So you're kind of like reflecting. Remember we learned about reflections. It's kind of like you're reflecting, but you're only reflecting the half of the graph that was negative, and you're reflecting it to make it positive. So let's take a look. Clear that. So here's an example. The line y equal, misclick. The line y equals x, if we didn't have absolute value bars, would have been this red line here. Pardon my little crookedness, but it would just be a diagonal red line. But when we take the absolute value, when we add that in, the part that's negative, which is this part over here, reflects up and becomes positive. So whatever these negative values were, they just switch. -1 becomes +1, -2 becomes +2, -3 becomes +3. Again, my line's not perfectly straight, but I hope you get the idea that the negative part is flipping up and becoming positive. So the most simple graph, it's just a big old V. And the left-hand side is a slope of -1. The right-hand side is a slope of +1. But we can take this and we can transform it the same way we learned about just a couple sections ago, transforming graphs by shifting left and right or up and down or stretching or shrinking or all that kind of stuff. So the general form for a absolute value function has a coefficient a, which talks about whether it's stretched or shrunk, and also whether it's opening upward or it's reflected and that's upside down, opening downward. The h refers to a shift left and right, and the k refers to a shift up and down. So the h and k together give you what's effectively called the vertex. H comma k is going to be your starting point or vertex. Basically, it normally starts at 0, 0 if you haven't changed it at all. So 0, 0 is your normal kind of not transition point, but like reflection point where it bounces off the axis. So if you shift the graph up or down or left or right, that point is going to change. So if this point here is 3, -2, that means my h is 3 and my k is -2. And then you can look at the slope. So a is going to be the slope. I went up 1/2, or even easier is up 2/1. So my slope, which is my a value, is going to be a 2. So the equation that I have graphed here, this equation is y equals 2 absolute value x minus 3, and the absolute value, and then -2. So we can look and determine what the changes are. So it's right 3, down 2, and stretched by a factor of 2. If this entire V shape would have been inverted and upside down, then that means the a value is negative, okay? And I want to comment real quick on one more thing. I'm going to clear everything off the screen. I want to comment on the idea that an absolute value can't be negative. So you say, wait a minute, Morgan, this graph clearly goes into the negatives, but it's an absolute value. So you have to remember that it's the absolute value part that can't be negative. But if you add or subtract something from it afterward, it can certainly end up negative. So the absolute value could come out to be some number, but if k is negative, you're then subtracting from whatever you had. And after you subtract, the answer itself could be negative, no problem. It's only the absolute value part that can't be negative. All right, so here we go. Last page of this notes is the examples. So we'll talk about the transitions to the function, and then we'll even graph a couple of those. So graph each function, state the domain and range, and describe how the graph is related to the graph. So it's actually the easiest way to start is to talk about the changes to the original graph. So for example, this means up 6 because it's a +6 at the very end outside of the brackets. So if I were to draw my graph, I would just go up to 6 and I would do this V shape, but I would start it here at 6. So that's a slope of +1. That's a slope of -1. There's my graph. I'm not going to add a lot of details, but if you had graph paper, obviously you want to make it really accurate. So what about domain and range? Well, the domain is how far it goes left and right, which in all cases for absolute values is going to be all real numbers. You can take the absolute value of any number, positive or negative, no issue at all. So domain is all real numbers. The range, though, for the absolute value function, it kind of stops right here, right? It doesn't go below whatever that point is. So in our case, domain is all reals. But the range on this one, at least, is y is greater than or equal to 6, because the y value of 6 is the lowest it gets. It's only the values above or equal to 6. Okay, cool. Let's do one more. Let's take a look. This x + 1 is inside the absolute value bars, which means it's a change to the x value left and right. And it's right 1. Again, this is helping to reinforce the idea that it's opposite of what you see. So if you see a -1, it means to the right one, because you have to plug in x = 1 to kind of like get back to your home base 0 vertex point. So if we draw our axis and we go over 1 unit, our graph will start right here, and then it will still have a slope of +1 on this side and -1 on this side. So that means the y-intercept is also going to be 1, because over 1 up 1, over 1 up 1. There it is. So the range is going to be y is greater than or equal to 0, because even though it moved left and right, it didn't change the height of the graph. And the domain, as before, is going to be all real numbers. Okay, so you can see what's happening when we have a shift up and down or a shift left and right. Let's do one more. Here we have a negative and a 1/4 in front. So this is going to be reflected. And it's going to be stretched by a factor of 1/4. Or you could say shrunk by a factor of 4. Those are equivalent. Stretching by 1/4 or shrinking by 4 are the same thing. So it's not moved left, right, or up or down. So it still starts in the center at 0, but it goes down instead of up. And it has a slope of 1/4. So we're going to go over 4 and then down 1. And then likewise on this side, over 4, down 1. So hopefully my graph kind of illustrates that. The slope is 1/4. So it's upside down because of the negative, and it's really, really flat with a low slope because of the 1/4 in the front. And domain and range. Domain, again, is all real numbers. I'm not going to write that. The range this time is, I'll write the range down here. Range, y is less than or equal to 0 because it's going downward instead of going upward. And then real fast, we'll finish it off with the last one. Why not? The -3 is inside the brackets, but when you take the absolute value of a negative, it actually becomes positive. So that negative, it doesn't even matter. This is going to be the exact same thing. And when you take the absolute value of 3, you just get 3. So this is going to be the same as 3 absolute value of x, which is actually, I think, kind of cool. So it's stretched by a factor of 3, starts at 0, 0. I'm going to just draw it in real quick here in the same color. So you're going to go up 3, and you're going to go over 1. Notice how to show this slope or the stretch factor, I just put 1 point and I label the values. So up 3 over 1, everyone can look and see that's up 3 over 1. And then it starts at the origin 0, 0. So domain and range are unchanged from the parent function. Domain will be all real numbers. Range will be y is bigger than or equal to 0. So anyway, looking at the equation, you can figure out the shifts and changes. And then from that, you can make the graph pretty easily and straightforward. Just look at the starting point, HK, and the slope, A. All right, have fun doing the extra credit problems. Good on you for doing extra credit, and I'll see you in class.